Hello everyone, welcome to another edition of Subject Math. Our topic today is calculations of heat and specific heat capacity. This is a continuation of the topic we started on measurement of heat. So this is the calculatory aspect of it. Okay, so I'm just going to start with the principle of heat exchange. According to that principle, heat is transferred from hot to cold object. So heat lost by a hot object or a hot body is equal to the heat gain by a cold body. The heat lost by a hot body or object is equal to heat gain by a cold body. Is equal to heat gain by a cold body. For instance, if I have hot water and then I decide to put ice block inside the hot water, you agree with me that the temperature of the hot water is higher than that of the cold water. So as a result, the hot water will give out heat to the cold water. So we're going to lose heat to the block. So it will lose heat, and you realize that the temperature will reduce because of the block that was introduced into it. So heat lost by that hot water will be equal to the heat gained by the block. So I want to believe that's very clear. So the first case 1, the first case we will be considering is this. Q is equal to MC change in theta. So for any question on heat and specific heat capacity, the case 1 is the use of this formula. This is one of the formulas we'll be using. In this case, this Q stands for quantity of heat. In case you are asked to calculate the quantity of heat, and it's usually in joules. M here stands for the mass, usually in kilogram. So if you are given a gram, so you have to convert to kilogram, except otherwise. C is the specific heat capacity of the body, and the unit is joules per kilogram per Kelvin or per Celsius. Then delta theta is equal to change in temperature. So in this case, usually you'll be given 2 temperatures, final and initial. So it's going to be the final and initial temperature, which can be written as theta 1 and theta 2. I want to believe that is very explanatory. Okay, a quick example of that is this. 500 grams of water is heated so that its temperature rises from 30 degrees C to 72 degrees C in 7 minutes. Take note, temperature rises from 30 to 72, 500 grams of water. Calculate the heat supplied per minute for 7 minutes. So the first thing we need to do is to write out our parameters. M is 500 grams. Theta 1, they said from 30 degrees to 72, that's theta 2, in 7 minutes. So instead calculate the heat supply per minute. Heat supply per minute. So the first thing we need to do is to calculate the heat supplied for 7 minutes, 500 grams, from 30 degrees to 72. This information here is for 7 minutes. So let's calculate the quantity of heat. But before we move on, we need to convert this to kilogram. That's 500 divided by 500 divided by 1000. This cancels this. So I have 0.2 kilogram. 5A1, 5A2, sorry, 0.5 kilogram. Sorry about that. 0.5 kilogram. So we are going to go ahead and apply our formula. Q is equals to MC change in theta. MC, I can write this as theta 2 minus theta 1. Our M here is 0.5. It has been changed from gram to kilogram. The C is the specific heat capacity, which is this, given from the question. Specific heat capacity of water is 4,200. So let's take note of that. Then theta 2 is 72 minus theta 1, which is 30. So 0.5 times 4,200 will give me 2,100. 72 minus 30, that's 40. 2,100 times 40 is equal to 88,200 joules. Don't forget, I told you that the quantity of heat is measured in joules. So this is the heat supplied for 7 minutes. But from the question, we have to calculate the heat supply per minute. Per minute. The heat supply per minute. That means for 1 minute. What's the quantity of heat supply? What's the amount of heat supply? Here is the heat supply for 7 minutes. So 1 minute. Heat supplied for 1 minute. For 1 minute will be equal to 88,000. 88,200 divided by 7. And that will give me 12,600 joules. So this is the amount of heat supplied per minute. So for 1 minute, 12,600 joules of heat was supplied. And then for 7 minutes, 88,200 joules of heat was supplied. I want to believe that this particular question is well understood, and then case 1 also is very, very clear now. So for case 2, when we have problems involving hot water and then cold water, or when you have problems involving water of 2 different temperatures, okay? So it's going to be MC theta is equals to MC theta. What that means is that, just like I said earlier, according to the principle, that heat lost by one body is equal to heat gained by the other. So here is the hot and here is cold. You can identify the hot or cold water via temperature, their temperatures. So I'm going to break this down. M is the mass. C is the specific heat capacity of water. The theta here is going to be theta 1 minus theta 3. And here is theta 3 minus theta 2. So for cases like this is applicable. So that is the standard formula for cases involving hot and cold water. An example of that is this: water of mass 120 gram at 50 degrees C is added to 200 gram of water at 10 degrees C. So let's pause there now. Water of mass 120 gram, 120 gram. Theta 1, which is the first temperature, is 50 degrees C. And another water of 200 gram, 200 gram. Theta 2, 10 degrees C. Now, you know I said something earlier that to identify which is the cold or hot water, you need to compare their temperatures. So if you look at this temperature here, you see it's higher than this. So that implies this is the hot water while this is the cold water. So I'm just going to label M hot and M cold. The question now says calculate the temperature of the mixture. That means calculate the final steady temperature of the mixture, which is theta 3. Okay, so you recall for case 2 involving hot and cold water. This is one of the formula we are going to use. MC theta 1 minus theta 3 is equals to MC theta 3 minus theta 2. This is for the hot and this is for the cold water. For the hot water and cold water. In theta 1 is the temperature of the water. Theta 3 is the final temperature of the mixture. Theta 2 is the temperature of the cold water. Theta 1 is the temperature of the hot water. So what we need to do now, our mass is given in grams, so we convert it to kilogram. Divide by 1000, that will give us 0.12 kg. While this also divide by 1000, will give us 0.2 kg. I want to believe that is also very clear. So M is equal to 0.12 times the C specific heat capacity is 4,200. I told you earlier, take note. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. But when it is in gram, it should be 4.2. So take note of that, 4.2 grams. 0.12 times, I'm going to use 4,200. Theta 1 here is 50. Theta 3, we don't know. So my M for the cold water is 0.2 times 4,200. Theta 3, we don't know. Theta 2 is the temperature of the cold object. So this multiplied by this will give me 504. So I have 50 minus theta 3 is equals to 0.2 times 4,200 will give me 840. Theta 3 minus 10. I want to believe we understand it to this level. So now we are going to expand That means we are opening the bracket. So 504 times 50, 504 times 50 will give me 25,200 minus 504 theta 3 is equals to 840 theta 3. This is 8,400. So I have 25,200. This comes to this side. 8,004. It's 40 theta 3. This goes to the other side. So we have 504 theta 3. So what I just did here was to collect like terms. So 25,200 plus 8,400. That is 33,600. 840 theta 3 plus 504 theta 3. That will give me 1,344 theta 3. So my theta 3 now will be 33,600 over 1,344, which will give me 25 degrees C. So the required temperature, the temperature of the mixture, theta 3 is equal to 25 degrees C. It's the same thing as the equilibrium temperature. Final or equilibrium temperature of the mixture. That is theta 3. Okay, so for case 3 involves a solid, a liquid, and then calorimeter, or a vessel, copper vessel. A calorimeter is used to measure specific heat capacities like a container. Okay, so we have solid, water, and calorimeter. And for case 3, the heat lost by the solid, this is the formula for case 3, is equals to heat gained by water plus heat gained by calorimeter. So this is the basic formula we'll be working with. I'm just going to rewrite that. So mc theta for solid is equals to mc theta of water plus mc theta of calorimeter. Now let me break it down again. mc theta. The theta in this case is theta 1 minus theta 3. The theta 3 is the specific heat capacity of the solid, which will be given. So this is for the solid. The specific heat capacity of the solid, will be given. The theta 3 is the final temperature of the mixture. Theta 1 is the temperature of the solid, which will also be given. So this m here stands for the mass of the water. C is specific heat capacity of the water, which will be given. Then the theta will be theta 3, that's the final temperature, the equilibrium temperature, minus theta 2. This theta 2 is the theta of the water, plus this is for water, this is for the solid, and lastly for the calorimeter. Now the mass of the calorimeter will be given, but the specific heat capacity will not be given. Since it's a copper vessel, it's usually a copper vessel or a copper container. So it is required of us to make use of the specific heat capacity of the solid, which we believe to be a metal. So here, the specific heat capacity of the calorimeter will be that of the solid. While the mass is the mass of the calorimeter. Take note of that. Then the theta is going to share the same theta as that of water, which is theta 3 minus theta 2. So take note of that also. It's sharing the same theta with water. So basically, this is what for case 3, this is the formula we'll be working with anytime we have questions involving solid, water, or a liquid, and then a copper vessel or probably a calorimeter. An example on that is this. A piece of copper ball of mass 20 grams. So the mass of copper is equal to 20 grams at 200 degrees C. So theta 1 is 200 degrees C. Is placed in a copper calorimeter of mass 60 grams. Copper calorimeter of mass 60 grams. So the mass of the calorimeter is equal to 60 grams, containing 50 grams of water. So let me write it here. Mass of water now is 50 grams. 50 grams at 30 degrees C. That's the second theta. Theta 2 is 30 degrees C, the second temperature. So ignoring heat losses, calculate the final steady temperature of the mixture. You recall that I said final steady temperature is our equilibrium temperature, which is theta 3. So the question is asking us to calculate theta 3. One very important thing I'd like us to note from this question is this. Our specific heat capacity is given in grams, joules per gram per Kelvin. Joules per gram per Kelvin. That means the mass will be left in grams. We don't need to convert it to kilograms. But in a case where we have 4,000, if you are given specific heat capacity of water as 4,200 joules per kilogram per Kelvin, in this case we will have to convert the masses to kilogram. I want to believe that is well explained. Okay, so we just move on. I have a mass of solid, which is copper. Mass of copper, specific capacity of copper, and theta 1 minus theta 3 of copper is equal to mass of water, specific heat capacity of water, theta 3 minus theta 2, plus mass of calorimeter, specific heat capacity, then theta 3 minus theta 2. You remember that formula? That's the formula I wrote earlier, that for case 3, this is the formula we will be working with. Okay? So let's just go ahead and write it out. So for mass of copper is 20 grams, So I'm going to write my 20 times calorimeter. Specific capacity of copper is 0.4. Theta 1 is 200. Theta 3, we don't know. Mass of copper is 60 grams. I told you earlier that the specific heat capacity of copper, of the calorimeter, will not be given. So instead, we use that of the solid, which is copper. So I'm going to use 0.4. Theta 3 is not given. My theta 2 is 30. Now, mass of the calorimeter here is 60 grams. Oh, sorry, I just did that of calorimeter, so I'll be doing that of water now, which is 50 grams times specific is 4.2. I'm just going to write it underneath here. So I have plus mass of water is 50 grams times specific heat capacity, that's 4.2. Theta 3 minus theta 2 is 30. So this is for copper, this is for calorimeter, and this is for water. It doesn't matter. I can decide to put calorimeter here, put water here, or water here, calorimeter here. Either way, it's still the same thing. The most important thing is that the water and calorimeter, they are on one side, while the solid is on the other side. Okay? Okay, so 20 times 0.8 and 20 times 0.4 will give me 8. So I have 200 minus theta 3 is equals to 60 times 0.4, that's 24. I have theta 3 minus 30. 50 times 4.2 here will give me 210. So I have theta 3 minus 30. So I'm just going to expand. 8 times this is 1600 minus 8 theta 3 is equals to 24. Theta 3 minus 24 times 30, that's 720, plus 210 times this, 210 theta 3 minus 210 times 30, that's 6300. I believe that is very clear. So we collect like terms. 1600, this comes to this side, plus 6300, 720 to this side, plus 720 is equals to 240, 24 theta 3 plus 8 theta 3 plus 210 theta 3. So addition of 1600 plus 6300 plus 720 will give me 8720. 24 theta 3 plus 8 theta 3 plus 210 theta 3 is equals to 242 theta 3. So theta 3 now is equals to 8620 over 242, and that's equals to 35.6 degrees centigrade. So our theta 3, which is the final steady temperature of the mixture, is equal to 35.6. So we come back here and write our value, which is theta 3 is equals to 35.6 degrees C. So I want to believe that is very, very well understood. case we will be considering, which is case 4, is that of waterfall. Waterfall. That's for water falling at an height. Initially, it possesses potential energy, but as it falls down, the potential energy is converted to kinetic energy. So for water falling at a height, or from a height, we have mc theta is equals to mgh, where h is the height in meters, g is the acceleration due to gravity. Acceleration due to gravity in meter per second squared. M is the mass. We are familiar with this. M, mass. C is the specific heat capacity of the water, and then theta is the temperature. So most of the time, for this case, we have just one theta, we have just one C and this. So usually you'll be asked to calculate the change in temperature while the water was at an height, and then by the time it fell on the ground, there will be a change in temperature. So quickly, we have an example here that I would like us to solve together. It says a waterfall is 1,260 meters high. So, solution. The height is 1,260 meters. Calculate the change in temperature. That's delta theta, change in T. Calculate the change in temperature. So, change in temperature, that is what we are calculating. We don't know it. Of a quantity of water that falls from the top to bottom of the waterfall. Neglect its losses to surrounding. Take G. We are given G as 10 meters per second squared, and we are given C, which is specific heat capacity, as 4,200 joule per kilogram per Kelvin. Okay, so we'll just go ahead and apply this our formula here for case 4. So I have mc change in theta is equals to mgh. From here, we are not given our masses, so I'm going to cancel out the m's. M cancel m since we don't have the masses. But if we have masses, we just have to put in the values of the mass that we're given. So m cancel m, so I have c change in theta is equals to gh. My change in theta, I don't know. My c is 4,200. Change in theta is equals to g. G is 10. H is 1,260. So I have 12,600. This is 4,200 change in theta. So change in theta now is 12,600 over 4,200. So this cancels this. This cancels this. Here 1, here 3. So my change in theta, change in temperature is 3 degrees C. You can see it's as simple as that. So the change in temperature is 3 degrees centigrade. Another thing I would like to discuss is the electrical method. Electrical method of calculating specific heat capacity. The heat gained is equal to heat energy supplied. Heat energy supplied by Probably the heater is equals to the heat gain by the water, or by the, yes, or heat gain by water. So Q is equals to H. So for cases like that, MC change in theta is equals to high VT. We use this when you have the current, the voltage, and the time. So we make use of this depending on your parameters, depending on what you are given. In some other cases, you may need to use this. This is the first one. In some other cases, you may do MC change in theta is equals to PT if you have the power and the time. Or when you are given current, you are given resistance and then the time, you can use this. Or you could also use this V square T over R. Probably when you have the voltage, the time, and the resistance. So you could use any of these four as far as the electrical method is concerned. Any of these four, depending on the parameter, depending on what and what you are given. So quickly, I'm just going to define these terms. I is equals to the current and is measured in ampere. V is the voltage supply measured in V volts. The time, that's the time taken, and so usually in seconds. P is power measured in watts. R is the resistance in ohms. I want to believe I have my I, V, I have T, P, and R. So I want to believe this is very, very explanatory. So quickly, I'm going to do an example on that. A very good example of that is this. A heating coil of resistance 20 ohms. Resistance is equals to 20 ohms. So we are given the resistance to be 20 ohms. Connected to a 220 volt source. The voltage is 220 volts. Is used to boil, take note, boil a certain quantity of water in a container of heat capacity. That is C, 100 joules per Kelvin. Heat capacity of the container, take note, for 2 minutes. So the time here is 2 minutes. If you convert 2 minutes to seconds, that's 2 times 60, which will give us 120 seconds. That will give us 120 seconds. If the initial temperature of the water is 40 degrees C, initial temperature, that's theta 1. It said calculate the mass of the water. If initial temperature is 40, then what is final temperature? Don't forget, I said we should underline boil. At boiling point, the temperature is 100 degrees C for the water at boiling point. So, we are asked to find the mass. So we are going to use one of the formulas I wrote out here. MC change in theta. Since we have our R, we have V, we have T. So the formula connecting the three is this, V squared T over R. So my M times C, specific heat capacity. Specific heat capacity of water is 4,200 joule per kilogram per Kelvin. That is what we are going to use. Specific heat capacity of water. Not this one. We are given specific heat capacity of the container to be this, but we are not using that. We are using that of water, since we are dealing with water. So that is 4,200 change in theta, that's 100 minus 40 is equals to v squared. Our v is 220, so I have 220 squared t is 120 seconds over r, which is 20 joules. So I have 4,200, this is 60, m is equals to, this will give me, this cancels this, here 1, here 6. 220 squared times 6 will give me 290,400. And this is 25,200 m, 290,400 all over. So my m here is equals to 1.15 kilogram. I want to believe that is very, very clear. So the mass of the water in the container is 1.15 kilogram, which is mass of water in the container. Here are some exercises for you to attempt. And don't forget to subscribe. Thank you.